In the previous lectures, we had seen the operational amplifier symbol, schematics, the reason for its name, and so on. And also, we have covered inverting and non-inverting operational amplifiers with open loop configuration. And also, we have covered comparator using operational amplifier. This one also with open loop configuration. So we will see the summary of the lectures so far what we have covered.
It has two input terminals. So one is called a non-inverting input terminal and another one is called inverting input terminal. And we have also biasing voltages V plus and V minus, and we have a single output. So we can have multiple inputs, but in the condition in this operational amplifier, mostly we will have only single output. And we have also seen the formula for output. V out is equal to A times A is the gain of this operational amplifier multiplied by the difference between the input voltages. So in practical applications, maybe we just ground either of these terminals and we apply the input to only to either of these plus or minus input terminals. So if you apply the input to this positive terminal, the output, for example, if you apply the sinusoidal wave, so the output you will get the sinusoidal wave, but it will be more amplified. Here there is no phase difference. That is why it's called non-inverting input terminal, because whenever you apply the input to this one, we are getting amplified output, but it's not getting inverted. But here, when you apply, if you ground this terminal, for example, let's say you grounded this one and you apply the input to this inverting input. So the same input you are applying here, but the output, what's happening? So instead of getting the phase is starting from here, the phase is starting, the signal is starting from here. It means the phase got inverted. That's why we call this as an inverting input terminal. Here the phase is not inverted. That's why it's called non-inverting input terminal. So these terms, please remember, because we are going to use these all the way in the operational amplifier topic. And there are different versions of ICs, and each IC is optimized for certain function. This is called, first we had seen the open loop configuration. Open loop means there is no feedback. Feedback means we are taking part of the output and feeding back to the input. So here there is no feedback. So we call this as an open loop configuration. So in the open loop configuration, we call first case one, that is a non-inverting amplifier. So it means we are grounding this inverting input, and then we are just applying the input only to this non-inverting input terminal, that is the positive one or the plus terminal. So we are getting the output. This is amplified, and at the same time there is no phase inversion. So the formula for the output is V out is equal to A times V1 minus V2. So here V2 is 0. So then if you just apply this in this formula, then A times V1, this is the formula for output. No phase difference between V1 and V out. So this is the V in or V1, and then this is the V out. That is why this is called a non-inverting. And case two, here we are grounding the other terminal. This is the positive terminal got grounded. That is the non-inverting input terminal. And the inverting input terminal, we are applying the input. So here we are getting the output, and here the output, you can see the formula, the same formula. V out is equal to A times V1 minus V2. Here V1 is equal to 0. So we have A times minus V2. So we just write here like this, minus A times V2. So the minus is indicating the phase is inverted. The phase got inverted. So here we are applying and we are getting amplified output, but it got inverted 180 degree. There is a 180 degree phase difference. And case 3 is differential amplifier. Here we are not grounding both terminals, either of the terminals or both terminals. We are applying input to both positive and negative. So here, so whatever the voltage is higher, then we are getting the output accordingly. For example, if this, let's say, here you can see this is the formula, right? V1 minus V2. So here V1 is 2 microvolt and V2 is 1 microvolt. So V1 minus V2, V1 is applying here and V2 is applying here. So the difference is positive. So we are getting the output without any phase difference. But in the other case, here this is another example. We will just see with some numbers so you can easily understand. So here we have the V1 as a 2 microvolt, V1 is a 2 microvolt and V2 as a 3 microvolt. So V1 minus V2, so that it means 2 minus 3, that is minus 1. So minus 1, that is the output here. So minus is indicating here there is a phase difference. So okay, you can always remember if V1 is greater than V2, there is no phase difference. If V1 is less than V2, then there is a phase difference. So if you remember this formula, then everything is okay. And this is, remember, this is open loop configuration. And we have one problem here. So we know each operational amplifier has the gain. It's indicated by the letter A. So A is 10 to the power 5 to 10 to the power 6. 10 to the power 5 to 10 to the power 6. Generally, this is the open loop gain of the operational amplifier. This is very high. So it means we have to really apply very small voltage in these input terminals. Even though you apply more voltages, it will easily get saturated. We had seen the voltage transfer curve. So here we had seen the voltage transfer curve. So after this is the differential input voltage. So even so, for example, maybe this is 1 microvolt and this is 2 microvolt and this is 3 microvolt and so on. So after certain point, even though you increase the input voltage, the output will not increase. So up to certain level, output will increase. This is the output in the y-axis. And after certain voltage of input, then output will get saturated to plus Vsat. So then that is, we want to operate the operational amplifier in this linear curve, in this linear region. So we should not reach this Vsat very fast for practical applications. We will see in detail in a while, but just remember that now. So output will easily get saturated to this positive or plus Vsat. Similarly, if you increase the differential input voltage in the minus, for example, here we had seen, right, in the previous slide. So in this case, we have the negative input voltage. So if you increase the negative input voltage, for example, minus 1 volt, minus 2 volt, minus 3 volt. So after certain level, the output voltage, this is the VO, the y-axis. So output voltage will get saturated. So what can we do for that? So we have to do some changes in the circuit. So this is what I mentioned here. I think we had seen this already last week. As soon as the input voltage goes beyond certain value, this is the input voltage goes beyond certain value, this point, then even though we increase the input, the output will get saturated to the plus Vsat. Similarly, for the negative side, the same. As soon as the negative input voltages, this is the negative input voltages, goes beyond certain threshold value, the output will get saturated to the minus Vsat. So we will move on now to the new topics. So operational amplifier has quite good characteristics. We will see the characteristics now. Because of that, it's useful in so many applications in electronics industry. So for example, we can use these operational amplifiers in filters. That is, if you use the up pump in the filters, that is called active filters. And we can use in oscillators to generate some frequencies, and waveform converters. You can convert sinusoidal wave into square wave. For example, this is the sinusoidal wave, right? And you can convert this sinusoidal wave into square wave. Square wave means what? Just it's like you're going to be a square. It's a positive side and this is the negative side. And you can make this as a triangular wave. So triangular means just shape is like a triangle, that's all. And we have sawtooth and so on. So we can also use this operational amplifier to perform the waveform conversion. And we can also use this operational amplifier for analog to digital and digital to analog conversions. And we can also use this as a clippers or clampers. So clippers means like you can rectify AC to DC, and clamper means you can boost the signal level. Okay, so this is useful in many applications. Remember, whenever this operational amplifier is used in open loop configuration, here there is no loop, no feedback. So what is the limitation? At that time, even if we apply a small input signal between these two input terminals, then you will find that the output will get saturated towards the positive or the negative biasing voltages. So I told you, so VD is V1 minus V2. So even though if this maybe this V1 is 1 microvolt, even if it changes to 1.5 microvolt or 2 microvolt, immediately the output will easily go to the saturated curve. You remember the curve, right? So this is the linear region and this is the saturation. So it will easily go to the saturation, but we want to operate the operational amplifier in a linear region. It should not reach this saturation region immediately. And so this is a drawback of this open loop configuration. So for this purpose, we are going to move to the feedback loop. Mostly we prefer to use this operational amplifier. This is a device, analog device with the feedback.